Okay. Hi, everyone. Welcome to your last Code Astro lesson. Very happy to be teaching this because this is my favorite lesson. And also, just wanted to mention that I'm going to be using Piazza for one of the activities to pull the answers. So please make sure you're logged in and you have the tab open. And yeah, welcome to this lesson. So, what exactly is code profiling? Code profiling is a way of analyzing the performance of your code in terms of runtime, memory allocation, and function execution frequency. And the primary goal is to analyze the performance bottlenecks and increase the speed and efficiency of your code. And in this lesson, we are gonna only talk about runtime profiling, but please use this as an inspiration to go check out memory profiling, and which can be done with modules like Memory Profiler and Trace and Alec. I don't know if that's how it's really pronounced, but that's what I call it. Yeah, so the links are in this notebook. Please go check them out later. So we are gonna talk about cProfile, which is a simple Python profiler, and it's built into the Python standard library. So it's already installed. You don't have to worry about it. And it gets us a C prefix from being a C extension version of the old Python profile module. At its core, it's just like any other timer. It's a like any runtime profiler for that matter is just a timer, like the timeout function. When you might have analyzed some small chunks of your code, you might have done this with like a timeout function where you go and create like start and stop timer. So this profiler also essentially does the same thing, but it does it all under the hood automatically for you, and it goes and inserts these small hooks or like timers into the Python interpreter when you start your code, and tracks your functions, and then outputs a detailed breakdown of your script. And also, just a reminder that this notebook can be found in the day 4 folder of Codastro. I recently pushed some changes to the repo. Please do a git pull so that you have the latest version of the notebook with you. Um, yeah, okay. So, and how do we run cProfile? So, to run cProfile, first of all, we need a Python script that calls the function or like a package in general that we want to analyze repeatedly, at least a few hundred times. So, because often there are different input parameters and that leads to variation in execution frequency, we want to sort of average that out. Or sometimes there are also inbuilt system functions that just come out on the top if you just run it like 2 or 3 times. So we want to make sure the functions that are taking the most time are reflected as such in our analysis. So, and for this lesson, we use a Python file called profile orbitize. And again, this file is in the day 4 folder. I'm just going to open that file. So this file is basically setting up the driver class, and then it's reading in some data, and then setting up some uh, parameters, and then it's basically sampling around 1,000 orbits. And notice that here we have set the number of cores to 1. So Orbitize by default is a parallelized code. And when we try to run a profiler on a parallelized code, it unnecessarily becomes very complicated. I'll come to that in a minute. Yeah, so when each of the cores will have a different profiler output if you run it on a parallelized code, and then you have to sort of combine them together and then analyze it. And anyway, the goal of profiling, at least in the runtime sense, is to figure out which functions take the longest rather than how efficiently your code parallelizes across cores. So turning off parallelization is a good idea. And to basically run cProfile, it's very simple. with Python, you would usually run the script like this, Python profile orbitize, but instead here we are attaching two additional arguments. This flag M basically calls the C profile and asks it to go and, attach all these hooks into the Python interpreter. And then this flag O is specifying the output file. Uh, if we don't do that, it basically dumps the output into the terminal, which is not very useful because we want to use it later to, sort of analyze what's going on. So yeah, and let's actually run it. I've already run it before, but let me just run it live. I hope you can see my terminal. So here I just ran this command, and then it's sampling around 1,000 orbits. It's gonna take a few seconds. Let's give it some time, but let me just introduce you to the module pstats, which is again like a Python inbuilt module. So this the output of the C profile is basically sort of like arranged in a way that pstats can analyze it well. And all you have to do is input pstats and then like call this read in the output file, and then it creates this object, my stats. From here, yeah. So what you can do is sort it by time. I'll come to different versions of time it has, and then just give this command print stats like top 5 functions. Say if you want to print out the top 5 longest running functions, and then let me just print that out. And let me just also minimize my terminal. Yeah. So it prints this out. Let's take like 5 seconds to just look at this. Yeah. So on line 1, it's just some metadata. And then here it says the number of function calls. So it's basically giving us a number of all the functions that were called, even in such a simple script that only took like 44 seconds to run. So you can see that there are so many functions. And then it says it's ordered by internal time. Internal time is essentially the same as this column. Tot time is total time. So I'll come to the difference between the cumulative time. So cum time is cumulative time, and n calls is the number of times a function was called, and it's printing out the function name here. For example, this is the function, but it also prints out the file name and the line number where this function is defined. So this is the output. And coming to the difference between total time and cumulative time, total time is basically how much time is spent in while executing the function. So this includes all the mathematical operations or like creation of arrays, anything that is not a call to another subfunction, but within that function. So that is basically the total time. And cumulative time is the execution time of that function, including calls to a subfunction. Yeah. And so once we have this output, which are the functions we want to target if we want to speed up our code? And for that, yeah, again, there are two different times. Which one do we really want to use, and which of the highest longest runtime function do we want to pick? So total time and cumulative time are both useful in their own way. Say we have a function like Newton solver wrapper. As you can see, it has a total time of 9 something seconds and also a cumulative time around that. And because cumulative time, by definition, includes time it takes to also call subfunctions, it's always going to be greater than your total time. Just something to remember. So Newton solver wrapper, for example, has a similar total time and cumulative time. That means it's none of the sub functions it's calling is really taking that much time. Rather, it's the execution of Newton solver wrapper itself that is taking all these 9 seconds. On the other hand, let's look at this function, calculate eccentricity anomalies, I think. Yeah, so this one, total time, it's taking 2.8 seconds, but cumulatively, it's taking around 13 seconds. So if we want to speed up this function, we have to dig in deeper and see which of the sub functions that it's calling is actually taking longer, because that the execution time of this function itself, just like the arithmetic operations or array creations, is just taking, like, say, 2.8 seconds. Yeah. P-stats comes with a lot of different filters that you can use. I think I have a link to the documentation somewhere. Please use that. But yeah, print stats, for here the order of the filter matters. For example, let's run this. So this is a command where it's sorting this object by time and then printing out top 15 functions and then applying this condition of it being a NumPy package. So we can go through this output. So initially, when it sorted it out, there were these many functions. And then due to the restriction, which of 15, where we asked it to pick 15 longest running functions, it came down to 15. And then we asked it to pick the NumPy functions out of those 15. So we only have one function at the end. On the other hand, if we reverse this order, yeah, now what it's doing is it's sorting this object by time, but then it's picking all the NumPy functions, and then it's applying the 15 cutoff. So you have like 15 NumPy functions. So we are at our first activity. So first activity is just to run the C profile on this Python script, so which is again in this folder. Let's take around maybe 10 minutes. People who are remote, I don't know if breakout rooms can be opened. Yeah. And people who are there, feel free to either work on your own or pair up with the person who's next to you. And please post the answers on the Piazza page. Just like number them 1, 2, 3, 4. And yeah, the instructions are here. Basically, just run it and try to answer these questions. Also, I forgot to mention, if you're running this notebook on the Collab, you'll have to upload the output file manually. Yeah.
Ruthie, there's a question here for you.
So I ran the command. Is the output of the command going to be in profiler underscore output.text, or will it be somewhere else?
So basically the output is the text file. So if you're using it on Collab, you have to upload that. Does that answer your question?
I got a text file. It's just kind of filled with jumbled.
Yeah. Yeah. Okay. Yeah. It's a binary file, so it's not human readable. And to basically analyze it, you have to use the pstats module and import it with this line. So basically, just run this notebook from code cell 1.
Repeat the question, please.
Oh, does this only work on Python functions, or if it was like a Python wrapper around another language?
You have to read it like
Would
this.
it have to do you have to use the other language kind of things?
So this profiler is like a Python module, so it only works on Python scripts. I don't know if basically if you're able to run it on Python, it should still work because you're attaching hooks in the Python interpreter. So yeah.
Thank you.
Yeah, no problem.
Is there a way to specifically select for non-built-in functions? Without specifying which package they are. We actually want them from.
No,
Okay,
no.
thank you.
Yeah. Yeah, it's PStats has a lot of features, but I've realized it's not as advanced as you'd like it to be. So I guess if you really want to play around with it, I would say use PStats and then use the output and save it like in a more manipulatable text file. And then you can play around with it like a CSV file, maybe.
Gotcha.
Yeah, feel free to start posting on Piazza. So just want to make sure there's enough time. So if people need more time, I'm just monitoring Piazza. So unless at least there are half answers there, I won't move on to the next thing. Okay. All right. Okay. Let's walk through the answers. Yeah. So for the first one, which function takes the most runtime, not including calls to subfunctions? Basically, we want to look at the total time, and then just gonna print out like first 5, and then this gives us Newton solver wrapper. Yeah. Yay. And then for the next one, including calls to subfunctions, we need the cumulative time. Yeah. So here, so these are the Python inbuilt ones, and like it says in the note, we can't really speed them up, so we want to focus on the arbitized ones. So the arbitized function that takes the most time, including calls to subfunctions, is run sampler. And then which function is called the most? For that, we use the end calls column and do this. Yeah. So it's the top function. So this one like has 2 parts. Like the first one is which function is called the most in general, and so it's is instance. And then if we want to specify arbitize, we can put it here, arbitize. And yeah, I think both transform samples and draw samples are the right answers because both of them are called equal number of times. And yeah, so if we had to speed up a function, what would we pick? So in general, we want to pick the one that has the highest total time, because if we pick the one that has the most cumulative time, essentially we're saying, oh, I want to speed this function up, but then it has so many sub-functions that are actually taking more time. So we have to sort of dig deeper. So at the bottom line, we want to pick a function that has most total time because that is the function that has all these array creation or arithmetic operations that are going on that are taking most time. So the answer would be the same as the answer to the first one, Newton solver wrapper. And I have another activity here. We just have 20 minutes more. Okay, we can try to dig into this a bit and then we'll come back in like 10 minutes. So I'll just walk you through this. So basically, like I said, if you have a function that has a long cumulative time and you want to investigate which of the subfunctions are actually taking long, you have this nice feature of pstats, which is print callees. So say, wait, we should have done, sorry guys, this is this one. Yeah. So we have this function log L, which has a very long cumulative time. And we want to investigate which sum function is taking the longest. So you just keep doing this and say you print this out. And based on this, you go off on like a hunt to figure out So here, for example, compute model is taking the highest cumulative time and you keep digging. So that is the activity. And maybe we take like around 7 to 8 minutes, and then we come back and discuss the answer, and then we wrap this up. Yeah. Okay. All right. It's just 10 more minutes left. So let's go through the answers. I'm going to cheat a bit, and I have my answer keys here. So I'm just going to walk you through that. So yeah, first you do log L, and then that tells you compute module is the culprit. And then you keep digging deeper. And once you do this one, let me actually do that. Oops, okay, come on. Yeah. Yeah. It takes us to Newton's solver wrapper, where the total time is very similar to the cumulative time. So this is the culprit. Yeah. Moving on. So we have another activity which we're not going to do here, but I just want to introduce you to this another function called print callers. So what we did was we digged into all the sub functions of a particular function, but we could also do the reverse, where say we think NumPy array creation is causing a lot of delays. So we can call all the functions that call NumPy array. And there's an activity where you figure out which arbitrize function calls or like creates the most NumPy arrays. Please do that in your free time. Another heads up, though, I guess you already noticed this when you were trying to do the previous activity. If you use the sorting on one of these, like print callers or print callies, it doesn't exactly work. It's because the object returned by print callers like is not exactly compatible with the sort uh, function. Yeah. So now that we know how to find the function that takes the longest, let's think about how to improve those functions. And let's take like 5 seconds to appreciate these memes, vintage memes. Okay. Yeah. Uh, um, So some of the strategies are like, so you have a couple of functions, but pick one or two slowest functions, because say one of the function is taking 50% of the runtime, and then if you split it by a factor of two, then you save 25% of the runtime. On the other hand, if there's a function that only takes like 10% of the runtime, and if you improve that by a factor of two, you only get like 5% saving of your runtime. And another important thing to think about is like the code readability. There's always things you can do, like remove some array creations or some variables and things like that. But at what cost? If the code becomes very hard to read, then it's very bug prone, and then in the long term, you're spending way more time, fixing that code. So there is also that factor to take into account. And here are like some simple ways. I would classify this in like 3 levels. Level 1 is just, like I said, eliminating all the computations that are not being used and using NumPy functions for matrix operations. NumPy, people have spent so many hours trying to optimize it for this specific use case. So I recommend using that and similar libraries that are optimized for specific use cases. And then avoid copying variables. We all tend to do that. And if there's a chance, you can use the same variable without having to make a new copy. Do that. That saves a bit of time. And then next one is to avoid using for and while loops. Yeah. And there's a way to avoid that. It's called vectorization, which you can do with NumPy. And this piece of code basically walks us through that. So here we have two arrays that are created, basically same array, just different name for comparison later. And then the goal is to add 5 to each of the numbers that are greater than 6. So I guess the most intuitive logical way is to, loop through the array and then, check for this condition, whether it's greater than 6, and then add 5. But the NumPy way to do it is like create a mask array. This basically uh, gives you an array which has like pointers to all the elements that are greater than 6, and then you can use that to just do this in one command. And yeah, the end result is the same, but the times are different. And for such a small array, you don't see that big of a difference. I have an extra activity here. You can just use like a simple time it function from a time module to time this and see. But then it starts scaling. It gets worse with the size of the array. So if you have like say 1,000 or more elements, then you really start seeing the speed up. And going back to this, level 2 of making your code faster is if you have MKL or BLAS, disable that. And I think this is covered in day 2 parallelization materials. And then another thing to remember is Python in general has all these inbuilt tolerance for precision of numbers. So if you can get away with a less precise number or like a variable, choose that because that saves time. And level 3 of this is to turn your Python code into C. So unless you are really desperate to speed that up, yeah, I mean, you don't have to do it. But then, yeah, C is like a much faster code. So yeah, we are at the end of our lesson, and I'll just leave you guys with this extra reading. And yeah, this walks you through some comments about runtime and memory allocation and just like how to estimate things. And like I introduced it in the beginning, there's a memory profiler that comes with Python. Feel free to check that out too. Yeah, thank you so much for listening. Are there any questions? All right. People in the Zoom? Any questions? Okay. Okay, I don't see any questions. Yeah. If you had any questions, always feel free to post on Piazza, and you can also reach out to me on Discord. Yeah.
Thank you.
Yeah, it was
Really
nice
interesting.
having all of you here. I hope you're having a great time. I know day 4 is a really busy time. Yeah, see you guys tomorrow. Good luck with your presentations. Bye.
Thank you.
Thank you.
Thank you.